So welcome to the first session on modeling thermal storage and standards. My name is Fouad Azizi, and I'll be chairing this session along with my co-chair, Dr. Karine Habshi. So this session is going to be actually a hybrid one. So we have in-person presentations and some online presentations. We will present them as we go. As I said, I'm Fouad Azizi, and I'm an associate professor of chemical engineering here at AUB. Our first presenter is actually in-person presentation, and her name is Rana Hamza. Rana is a mechanical engineer at EDL, Électricité du Liban. Rana has a diploma in mechanical engineering from Lebanese University, the Faculty of Engineering, and a master's degree in renewable energy from the Lebanese University, Faculty of Engineering, and the University of St. Joseph, the Faculty of Engineering as well. She will be speaking on the utilization of mobilized thermal energy storage system for heating or cooling the Lebanese University campus, simulation, economic, and environmental analysis. The floor is yours.
Thank you. Dear organizers and AUB staff, ladies and gentlemen, thank you for hosting me in this event. My name is Rana Hamza, and I am here to present to you the study concerning the utilization of mobilized thermal energy storage MTS system for heating, cooling of Lebanese University campus. The study will conduct a design, simulation, economic, and environmental analysis. Okay, the presentation includes an introduction, a quick state of the art of MTS system, the objectives of our study. We have a description of our case study, design of different heat exchangers, simulation of the different phases, the efficiency of the system, economic and environmental assessment, and finally, a conclusion. First, as we all know, energy demands worldwide increasing. And with the increase of energy demands, we have an increase in waste heat. Actually, 37% of global energy consumption goes to industrial sector. 33% of industrial energy is dissipated as waste heat, which is a huge number. On the other hand, residential sector is responsible for consuming about 40% of global energy. Base heating and cooling alone compose 40% of residential sector consumption, which is also a huge number. In our study, we use the Mobilized Thermal Energy Storage System, abbreviated with MTS, to both valorize waste heat and, second, reduce residential sector consumption by covering heating, cooling load, and water heating. MTS system is abbreviated in this figure. It is defined mainly by three components. We have the waste heat source, we have the container configuration. The container is transported, that's why we call it mobilized, to the end user, and we have the storage materials, which are basically phase change materials. A quick state of the art of MTS systems start by waste heat sources. In most applications, the waste heat sources are in gaseous state with temperature higher than 100 degrees Celsius. Most used phase change materials are sugar alcohol and salt hydrates. Erythritol is the most used phase change material, which will be used in my study. It is the highest energy density, and it has a high latent heat and is relatively cheap. Okay, the container configuration could be direct, where the heat transfer fluid and the phase change material are mixed directly. The phase change material density is higher than that of thermal oil to make sure of phase separation. And we have the indirect contact right here. We have the indirect contact tube and shell, where the PCM are placed in the shell and heat transfer fluid flows inside the tube, or the encapsulated type, where the phase change material are encapsulated in subcontainers and the heat transfer fluid flows around. Okay, the objectives of our study is a large scale PCM capacity or MTS system capacity of about 7 megawatt hour. Our case study is a Lebanese case study. In this study, we designed the different heat exchangers of the system. We conduct a simulation for the different phases. We study the effect of heat transfer fluid flow and waste heat potential on the charging time and efficiency. and we calculate the system efficiency and its effect on the power plant. And finally, we have an economical and environmental evaluation of the system. Okay, our case study, as we know that Lebanon is one of the countries that has a shortage in electricity, and we have high rise in fossil fuels cost, and we have benefit to lower our dependence on fossil fuels. That's why we choose Lebanon for our case study. Okay, in our case study, the waste heat will be the fumes of a Lebanese power plant. The end user will be the Lebanese University main campus in Hadas. And we choose erythritol as phase change material or storage materials. The container will charge in the Lebanese power plant and discharge in Hadas, and will return after discharging to the Lebanese power plant to start a new cycle. Okay, the MTS cycle is abbreviated, is showed in this figure. We have the recovery heat exchanger where the fumes transfer heat to heat transfer fluid. Heat transfer fluid in its turn transfer heat to PCM in the storage heat exchanger. The container will be transported to Hadas where it will have self-discharging due to convection, natural and forced convection. And in Hadas, we have the heat transfer fluid will take heat from phase change material and then restitute heat to circulating water system. The circulating water system will pass through absorption chillers to produce cooling, or through heating radiators to produce heating, or through domestic hot water heat exchanger to produce sanitary hot water. Okay, the waste heat potential is represented in this chart. It is a typical year, a chart for a typical year on hourly basis. The mean potential of the fumes is about 10.4 megawatt. The maximum is about 21.4 megawatt, and the minimum is about 0.8. The average temperature, waste heat temperature, is about 150 degrees. During the year, the energy wasted is about 91,000 megawatt hour. The load profile was estimated based on the different faculties, areas, and dorms. The load consumption during the same typical year is about 19,000 megawatt hour per year. Okay, the heat exchanger, we use the log mean temperature difference method and NTU method to calculate the heat exchanger areas and the efficiency. We have the recovery heat exchanger and the restitution heat exchanger are both the counterflow tubular heat exchangers. In the recovery heat exchanger, the shell will be the chimney of nominal diameter about 2.2 meters, and the tube where the heat transfer fluid flows is about 10 centimeters of diameter. The restitution heat exchanger, also counterflow tubular, the nominal diameter of heat transfer fluid which passes in the shell is about 25 centimeters, and the nominal diameter of the circulating water tube is about 11.5 centimeters. Okay, the storage heat exchanger, which is inside a container, 20 feet ISO container. I choose to encapsulate phase change material in about 1,080 aluminum tubes, which the total mass of the PCM is about 30 tons. The heat transfer fluid passes from below and exits from above. We have about 5.5 tons of heat transfer fluid flowing around. Okay, our simulation, first simulation is the charging in the charging phase. We can see that the phase change material or erythritol temperature increase until reaching its melting point at 118 degrees Celsius. At this point, the melting process begins, where we have the storage of latent heat. The latent heat storage or the melting is completed at about 5,500 seconds. Then, after the complete melting, the PCM are storing sensible heat until reaching 130 degrees Celsius. The mass flow and the oil tank temperature increase with the increase of phase change material temperature until reaching the oil flow set. Okay, this is the charging phase. In the charging phase, we have two factors that are important, which is the mass flow set point or maximum heat transfer fluid, and we have the waste heat potential. By increasing the heat transfer fluid flow to its double value, about 200 kilogram per second, we make the simulation and we get an increase in the efficiency by 8% charging efficiency, and we have a decrease in charging time but by about 29%. It's an important agent in the LTES system. The simulation was repeated for higher waste heat potential. We conclude that we have a slight decrease in charging time by about 3.65%, and we have an increase or also decrease in charging efficiency by 10%. In this table, we have the different results of our simulation. We can see that our charging efficiency range between 9.9 and 83.5. Okay, and the self-discharging, which I mentioned before, we have during transportation, we have natural convection or forced convection. We have, of course, a convection factor. The temperature of MTS system decreased to about 129 degrees Celsius. We repeated the simulation for different rock wool thickness, which is the isolation material. We get that 4 centimeters of rock wool is enough for our case for isolation. Okay, and the restitution heat exchanger, we can recognize 3 powers. We have the useful power, which is the cooling power or heating power, or hot water, sanitary hot water power. We have the restitution power, which is the useful power over the efficiency of the systems used, absorption chiller or radiator or heat exchanger hot water. And we have the discharge power of PCM. The discharge power of PCM is equal to restitution power over the efficiency of the heat exchanger. For each discharge power, we conduct a simulation, but right now we will put an example because they are many. For 6.96 megawatt discharge power, we have this graph, the PCM temperature decrease until its solidification temperature at 118 degrees Celsius. At this time, the solidification process begins until ending at about 2,400 seconds, and then the temperature decreased by releasing sensible heat until the end of discharging at 95 degrees Celsius. Okay, the different simulation for different discharge power is represented in this table. We can see that the discharge efficiency range between 66.25 and 91.24. The heat exchanger area is different from winter to summer. We optimize the surface, the area, and we have different area for heat exchanger of sanitary hot water. Okay, the whole cycle of MTS system is represented here. The charging, I forget to tell you that the charging capacity is 7.05 megawatt hour. In this part, we have the charging. At self-discharging, the capacity decreased to 7.03 megawatt hour. And after discharging, we have a capacity of about 0.9 megawatt hour. The efficiency of the system. The efficiency of the different stages of the system is represented here. The charging phase, as we mentioned before, the efficiency range between 9.92 and 83.5. During transportation, it's 0.15%. Every additional hour causes the decrease of efficiency by 0.11. And in the discharging phase, the efficiency range between 66.25 and 91.24. The efficiency of the power plant, without using the MTS system, the efficiency of the power plant is about 30.21%. With the use of MTS, the efficiency increased by about 0.78%, which is equivalent to producing about 2.16 megawatt. The profits from this efficiency increase are about 2.16 million USD. Economic and environmental assessment. The economic assessment was conducted for 2 cases. The first case is for heating only, and the second case for heating and cooling. In the first case, the payback period is about 3 years, 10 months. The net present value is 2.7 million USD, and the cost of heating, which is the most important result we get is 0.02 USD per kilowatt hour. By using MTS system for both heating and cooling, the payback period increased a little bit. It's about 4 years, 1 month. And the net present value is 2.83. The operation cost is 0.01 USD per kilowatt hour. Okay, the diesel savings in Lebanese University campus, they use fired boilers for heating and for water, sanitary water heating also. So the savings from from diesel is about 1.09 million liters per year. We have, as we know that the MTS system will be transported, so we have diesel consumption for trucks or lorries. It's about 140,000 liters. By subtracting the two numbers, we get a total saving of about 0.95 million liters diesel per year. Environmental assessment, the electricity savings is about 2,938 because in the campus they run the absorption, they run the chillers, electrical chillers. They have chillers, not absorption chillers. They run chillers on electricity, so the savings from electricity is about 2,900 megawatt hour per year. And the diesel savings, as we mentioned in the previous slide, is 0.95 million liters. So the total CO2 reduced is about 3,400 tons of CO2 reduced per year from our system. By comparing MTS system with the different heating system or conventional heating system, we can see that the MTS system has the lowest cost of heating with about 0.02 USD per kilowatt hour among the other heating systems. And as a conclusion, we conclude from our system that is feasible, it is profitable. We increase the efficiency of the power plant by about 0.78%. The different efficiencies are set. In the presentation, we have a saving of 0.95 million liters of diesel. The most important parameter is the maximum oil flow. And finally, compared to different heating system, MTS has the lowest energy cost of 0.01 USD per kilowatt hour. Thank you. Thank you for listening.
Thank you, Rana. So we do have time for some questions.
Thank you for your presentation. Actually, I teach as well at the Lebanese University in Hadass. My query is about the heat source from where you will be importing the heat. What is the closest heat station?
It's a boiler, fire boiler.
So from on-site, from the on-site fire boiler?
This power plant has 3 boilers. The fumes that are, or exhaust gas from the boiler chimney are the waste heat source.
Yeah, but what is the closest one to the campus?
Actually, it's, we cannot just publicate the name.
Yeah,
we
because
have an NDA. So.
How many kilometers is far?
It's 23.
Far from the campus.
Yes.
With the traffic that in that area, so did you calculate the drop in heat for each commuting from the heat storage heat source to the campus? How many hours are you going to employ?
Self-discharging simulation, we take an average of 2.5 hours from end of the charging until the beginning of discharging, about 2.5 hours. We take self-discharging. Of course, in Lebanon, we have many problems. In case we want to execute this project, but this can be managed later under the name of operation plan or operation management. I think like that.
Okay, thank you.
Thank you. Another question?
علي أبو صالح من ال LAU. بس نحن حابين نسألك لأنه نحن هلا أخذين على حالنا
Can you speak in
I
English?
can speak in English, yes. So this year is our final year as mechanical engineers, and we are introduced to thermal system storages as our FYP. So we have a lot of questions in this field. So first of all, about the shell and tube heat exchanger. It was a simple design where you chose 1,080 tubes of
Didn't hear what.
the shell and tube heat exchanger.
Oh, shell and tube.
The shell and tube heat exchanger.
Restitution.
Hmm?
And the recovery or restitution?
And the
Recovery, restitution.
and the recovery process.
Recovery, okay.
So the latent heat energy storage.
Yes, okay.
So about the setup that you chose, it constituted of tubes and the shell, only tubes and shell.
Yes.
Were you able to come up with a design that was enhanced, for example, using a double pipe instead of the singular tubes and the addition of fins? Were you able to optimize the design?
Yes, of course, it's a very important question. In my study, we have in our results the length of the heat exchanger is very high. So we take the optimization for another study because the design of the heat exchanger alone, you can make a thesis of it. You know what? But what is important to me in my study is the energy result and the efficiency, the heat exchanger area to continue calculation. But of course, the design can be optimized. The storage heat exchanger design could be optimized. Many other studies could be conducted starting from this study. The addition of fins can decrease the length of heat exchanger. For example, if you have a heat exchanger of 500 meters, it's huge. So of course you add fins, you can, for example, double entering, double outlet. Yes, you can optimize the design.
One more question
Yes.
about the hot fluid, the entering hot fluid.
Yes.
Were you able to apply any degrees of simulation by increasing temperatures or flow rates? And if you did, what was the major effect of these?
Is the question?
About the heat transfer fluid that was entering the shell, since the PCMs were stored inside the tube.
Recovery, because the heat-
Recovery,
and the recovery.
recovery. The
Heat
heat
transfer fluid entering
entering the
tube,
shell,
not
yeah.
entering the tube.
entering the tube.
The fumes are in the shell.
Okay. Were you able to alter the mass flow rate entering and the degree, the temperature of the entering heat fluid?
Heat transfer fluid flow varies according to temperature because at the inlet or at the beginning of the simulation, the heat transfer fluid is cool. You have a different mass flow rate. As the temperature of oil increase, the mass flow rate increase. But we have a set point. You can't just continue increasing the heat transfer fluid flow. So when you get the set point of heat transfer fluid or the maximum value of heat transfer fluid, you get the simulation continue at this flow rate. You can't increase more.
Okay, thank you.
As you can see in my simulation that I studied the heat transfer fluid effect, I doubled the set point. When you double the set points, you get an increase in efficiency and decrease in charging time.
Thank you.
We have time for one very quick question, if there is one. Okay, so join me in thanking the speaker.
Thank you.